talked about the advantages of Jfet partially. Okay, every now and then when we are discussing some topic, we said that what are its advantages. We're just going to list them down in series now. Okay, the first thing is it has a very high input impedance. So if I'm asking you a question on the advantages of Jfet, okay, you basically have to take these points. Okay, that's of the order of 100 mega ohms. So what impact does it have having a high impedance, okay, input impedance? It's simple. That means that the charge carriers that we have are completely because of the biasing, and if we have any kind of noise because of this high input impedance, I hope you understand, it's a form of resistance, but impedance usually depends on the frequency. So this is basically nothing but a very high input impedance. It straight away signifies that if you have got any kind of noise, this is not going to go through, okay, because of the high impedance. Okay, so this restricts noise. Okay, so what we can say is that this in general permits high degree uh, isolation. Okay, isolation between the input and the output circuit. So output circuit will have the signals that you need. Okay, input and output. So basically what happens is if there is a no noise as such, you can basically get a very clean signal, which is only because of the charge carrier that is flowing because of the biasing. Okay, so one of the important point to note is that the operation of Jfet depends, okay, on the bulk materials. Okay, bulk material current carrier, you can say. Basically that is the property of the material because of which the current is being carried. Okay, so what happens is if there is any kind of noise as such because of any other part of the circuit, that is not carried forward. Okay, so what happens is the noise of the tubes, let's say the tubes are attached, okay, are not carried forward. Okay, are not carried forward. So I think it's quite straightforward. It is more or less complementing the first point. It depends on the charge carrier property of the material, and it doesn't really depend on any other circuit part. So that means you'll have minimum of noise in these kind of devices. Okay, JFET has a negative coefficient of temperature. Okay, or basically you can say temperature coefficient of resistance. Negative temperature coefficient of resistance. Now you might think that, okay, what is the significance of this? It means that if you are increasing the temperature, okay, the resistance goes the other side. So what happens is that this will actually avoid the risk of thermal runaway. Okay, so temperature and coefficient resistance does not move in the same direction. Okay, so even if you can actually have a temperature dependent JFET system. Okay, and if you are considering that let's say you will be having a large number of charge carriers, okay, at room temperature, that is not possible, because if the temperature is low, let's say at room temperature, the resistance is very high. So if the resistance is high, you don't have any kind of signal or any kind of noise which basically flows away. Okay, so this avoids thermal runaway or thermal. Okay, we can have done thermal runaway. So I hope you understand, thermal runaway means that you won't have a breakdown because of temperature if you can control it. Okay, and then it has a high power gain. That is, I think, very important, because that is based on which we are actually using the device. Power gain is an important factor. So we don't need driver stages. So when we studied about multi-junction transistor or multi-stage transistors, we actually had one transistor, but then we needed to increase the signal to a higher value, and for that actually we needed one more transistor. These are all multi-stage transistors. Here we really don't need it, okay, because it already has a very good gain. So we don't need a number of stages here. A single stage can actually give you an appreciable amount of gain. Okay? And of course, some basic parameters are, it has a longer life. smaller size, very compact, okay, and high efficiency, and high efficiency. So all of you please note down these points, okay. This might be around 2 to 3 marks question, so whenever you are getting some question based on points, probably you can take just 2 points for 1 mark, okay. So I think that is important. So this is the advantages of Jfet. I just listed them down because you know you already studied it, but I think it's important that we just do it once, okay. Next I'm going to do something which is called biasing, Jfet biasing, but then here I'm not going to go into too much detail because you know biasing is actually a very big topic, but here we're just going to talk about the basic part of Jfet biasing, okay. And I hope all of you understand what is biasing. Whenever we talk about biasing, it means that we are going to apply some kind of voltage, okay, and based on which the charges are usually going to flow, okay, and that is what is biasing is all about, okay. So you know if you are considering n channel, okay, JFET, gate must be negative with respect to source, must be negative with respect to source. So if you remember this, that what happens usually is that whenever you are having a gate in between, there is an AND channel, so that means the gate junction would be p type, right? So if the gate junction is p type and we are actually having an AND channel, what happens is that the uh, biasing is important because gate must be negative if it is connected to a positive terminal. So because that is what JFET is all about, it basically works in the reverse bias connection, okay. So what we can do is we can bias using a battery, okay, battery in the gate circuit, in the gate circuit. So on the gate side we can actually put up a battery, okay, that can be done, or we can actually use a circuit, or we can use a circuit called biasing circuit. So, you know what happens usually is batteries are usually costly, okay, at the same time you need to maintain them. So as a result of which sometimes this biasing using a battery is avoided, okay. So this is not a very popular method, okay, and actually it needs a very long number of frequent replacements, okay. So maybe I can write down this note: battery requires replacement, and okay, it basically requires maintenance, okay, and it's costly of course, so cost, hence avoid it, but still nevertheless we can actually always do it by using this, okay. So if we're just talking about biasing battery, okay, I can actually probably show you the circuit here, okay. So maybe we can just draw some circuits now. So I'm just going to draw some circuits here, okay, very important. So if you're basically using a battery, the circuit that you have to draw is something like this, okay. So let me draw the circuit for you. So this is the output circuit, okay. So the circuits, you know, you have to just keep practicing. Okay, so what happens usually is you are basically going to have a load resistance, okay. This is one resistance here, and at the input terminal also we are definitely going to use some resistance to control the current, okay, that is important, okay. So if we just do this, we are basically going to have a signal at this end. So this end we are going to have a signal, okay, and then this is your RG, the gate resistance, okay, and you are going to bias it using a battery. So this is the battery that you're going to use. So this is the part that you're going to use if you are biasing the input using a battery, okay. So let me just consider an N channel, okay. So if I use an N channel, I can put here this sign, okay, and this is your gate terminal. So the voltage that you measure across these gate will be nothing but VGS, gate and source terminal, okay. This is the resistance which is connected across the drain terminal, and this is plus VDD, okay. So that's it, that's the circuit that we have. Okay, and then if we are considering basically a battery, okay, let me take this image as one. Okay, so this is your first image. Okay, we are using a battery here. So if we are using a battery, what we do is usually we are just connecting it to the input and we are actually biasing the gate. Okay, of course we have a voltage drop across gate source, that's a different part that we actually do in our calculation. So I think this circuit is also quite clear. It's just similar to a transistor. It's like you are actually having this part connected to the ground. Okay, and this is how it is represented usually. Okay. Okay. So that was using the battery. Okay, but then there is also something which we call as the biasing circuit. Okay, so let me just give you a note about biasing circuit. That's the second part. Okay, biasing circuit. Let's just talk a bit about biasing circuit. Now biasing circuit also, there are different ways of biasing it. Okay, so if you just consider battery, okay, that is the first one. Okay, and if you are considering the biasing circuit, we are talking about the second one here. Okay, so let's just talk about the second one, the biasing circuit. Biasing circuit also, there are different ways of making the circuit so that you can actually have the biasing. Okay, so what usually happens is it basically uh, you are already having a supply voltage at this end, VDD, that's the drain voltage. Now this voltage basically can be used to even bias the input terminal, and that is what is done here in this case. Okay, so it basically uses supply voltage, okay, VDD, and just put the base later, okay, to provide the necessary bias. Okay, necessary bias. So this is important. There are two methods to use. Okay, there are two methods. Please make your sentences properly, just frame them. Okay, the first method is, I basically call it as self bias. Self bias. Okay, so I'll just show you the circuit diagram for self bias. Okay, and then we basically have the resistor which is there will act as the bias. Okay, so resistor R, I will show you which is that resistor, is the bias resistor, is the bias. This is important, this is one part. And what happens is there is a capacitor, the capacitor acts as a bypass for the AC signal. So if you're basically having a DC signal and you want to bypass the AC signal, you can actually use the capacitor in the circuit. So this is something which I'm going to show you. Okay, I'm just going to draw that figure. Okay, so that is self bias. And then there is one more which is called the potential divider method. So probably just going to do this, draw the diagram. Okay. The other one is potential divider method. Potential divider method. Let's just draw two circuits there. Okay, and the first circuit that I'm going to draw is for the self bias part. Okay, so in the self bias part, I'm not going to use any kind of battery here. I'm going to use this voltage to actually supply the biasing part. Okay, so what I'm going to do is this. Okay, so let's just draw the circuit. So probably I can just copy this, okay, paste it, and then do the necessary changes. So I'm just doing the self bias part here. Okay, so you already have a VDD here. Okay, and we don't have any biasing here, so we'll rub this part. Okay, so if we rub this part, we just have got the grounded part here, so we are not going to use any kind of input battery here. So you can relate it with the previous diagram. Okay, we have got VDD, we have got RD. Okay, and then we also have the drain source voltage. Okay, let me just make this. This is voltage across the drain and the source. I think we all know this. This is drain, this is source, this is gate, right? You don't really need to label this way, but I think you can do it sometime, okay, so that things are a bit clear to you. What is done here is basically a resistor is connected here. Okay, a resistor is connected here. Okay, so let's just try to connect that resistor now. Okay, what I'm going to do is I'm going to make a resistor here. Okay, so this is the resistor that we have, and there is a capacitor which is also connected. So we have one. Let's draw this. So this is a capacitor which is actually connected across this terminal. Okay. Okay. So this is nothing but we are writing it down as CS. So this capacitor that I'm talking about here is this CS. Okay. And then we have got a resistor which is nothing but RS. Okay. So maybe we can take the higher potential and the lower potential part. So this is RS. Okay, this is the RS that I'm talking about here. Okay, so you look into this now, and let's just look into the circuit again. What happens is the aim is to provide a biasing to the gate. Okay, so that you will basically have the current flowing across the drain and the source. Okay, the channel will actually allow the current to flow. So what happens is, if you look into the circuit, okay, if we just have the circuit, let me go to some previous lectures, and we already have the circuit there. I hope I can find it out somewhere. Okay, yeah, I think this is there. Okay, so you see this is the circuit. Okay, and this circuit is actually connected to the output terminal. Okay, so if we do that, okay, this is not the exact one, but if we do that, what happens is the whatever biasing you're applying here, it has an impact on the input. Okay, so this is what we're doing here. Okay, so if we just go back here. Okay, so this is what is being done. So you have a voltage being supplied. If there is any kind of AC component, this will be actually bypassed by here. Okay, this will be basically acting as an AC filter, and you have only the DC component which is working along this. Okay, so this particular voltage drop across, or the potential across this RS, will act as a biasing for the gate terminal, and this is what is self bias is all about. Okay, so this is number 2 1. This is self biasing. What you have to do, you have to connect a resistor in the output terminal, exclude the AC signal from there. Okay, and then based on this, the input will be actually biased, and you don't need to use any kind of battery at the input. Okay, so you know, output terminal, if you're using a AC signal here, you can get the DC component and use it for biasing the input, so that is possible. Okay, and the final one is the potential divider method. Okay, so let's try to learn that now. Okay, so let me just I will take the same circuit and try to redesign it. Okay, so I think I cannot use it here, right? So let me use a new page. So this is the potential divider method, and then I'm going to use, and let's see what is done here. Okay, so here actually what happens is, just again rub this part off. Okay, and okay, I will probably take the other image. Okay, the other image will be more easy because the changes are less there. Okay, so let's go to this previous page, take up this. Okay, so let me just re-level everything. Okay, I'll just probably take this as R1 and R2, those kind of structures will be okay. Okay, so we have the signal here, and then we have got R2 here. I've got R2 here. Okay, the most interesting part is here it is VDD, and we are connecting this same VDD across this terminal. We are using the voltage divider method. Okay, so if you remember from your lower classes, voltage divider method, if you are having two resistances connected in series, and if you are applying a voltage across this, the voltage has divided across these two resistors, right? So let me just consider this. Okay. And this one I will take it as R1. So this is R1. So during exam circuit is more important, try to remember that. Okay. And if I am applying a VDD here, the VDD is also across this end, so probably what I will do is I will write down here plus VDD across both the terminals. We are actually having a potential VDD. Okay, everything else more or less remains the same. This is RS and that's all. Okay, that's fine. This is plus and minus, and this is nothing but V2 voltage. So this is the voltage which is actually acting along the gate. Okay, so now just look into this circuit. This is almost similar to the previous one. The only difference is I am not applying the biasing across this RS now. That was the self biasing part. What I do is I'll extend this part and actually connect it with the input terminal. Okay, and then I'm going to use number of resistors. See, this is R1, R2, depends on what resistance you have. Okay, based on that configuration you can have a number of resistors which are connected in series. So here I'm just showing two resistors being connected. You have got voltage divided across this part, because the voltage that is needed to run the gate at the input terminal might not be as high compared to the voltage that you need at the drain circuit. Depends on what is the configuration, right? So what usually is done is we are actually connecting an appropriate resistor R1 and we are taking another resistor R2. So whatever is the voltage across R2, that is what is being used for the input terminal. Okay, so this is being used for the input terminal. Okay, so this is important. So this is what is the voltage divider or the potential divider method is. Okay, so this is number 2. Okay, so this is potential divider method. Potential divider method. So as far as biasing is concerned, if you take up anything on biasing on a particular circuit, you are going to get a lot of content that you need to study. Okay, but then since this is the syllabus that we have right now, and of course we cannot go beyond this because it's a bit too much, right? So we'll just stop here with biasing part. Okay, so this is all about biasing in a transistor. Okay, so what you have to do in biasing is you have to remember these circuits. First you have to understand what biasing we are talking about. First is the biasing by a battery at the input. Usually not done because battery requires replacement, it's costly, so it's avoided. But if you're considering biasing at the output, okay, that means VDD, this can be used to bias the gate. And what we can do is we can do two methods. One is a self biasing and one is the potential divider method. So in self biasing what happens is we are actually connecting a resistor here, okay, and then whatever is voltage across this is basically used as the gate voltage. On the potential divider method, we actually are having this voltage being distributed between the input and the output across the same terminal. So what happens is that if you're connecting a resistor, appropriate resistor, depending on the configuration that you have for the circuit, you can actually divide the voltage between this part and this part. And this is the voltage that is being used to bias the gate or run the gate.